If you're not part of the solution, you're part of the precipitate. What is a solution? Well, in simple terms, a solution is just nothing more than a homogeneous mixture of a solute dissolved into a solvent. Well, that answers all your questions, right? Bye! Just kidding. A solution is what you get when you take a substance and put it in with a solvent. A solvent which can rip apart the attractive forces between the solute particles and disperse them evenly into a mixture. That's why it's called homogeneous, because all the particles are spread out evenly throughout the entire mixture. Here, for example, we have some sodium chloride, some positive sodium ions and some negative chloride ions. That is the solute. The solvent is the water. Now, why can water dissolve salt? Here's why. Salt is made of positive and negative ions. Water, being a polar molecule, has partially negative and partially positive ends. Therefore, the partially negative end of the water molecule, the oxygen end, is attracted to the positive ion, specifically the positive sodium ions. That's why we have the sodium ion and these oxygens surrounding it. The partially positive end of the water molecule, the hydrogen, is attracted to the negative ions, which is why we have these negative chloride ions with the hydrogen end of the water molecules surrounding them. Water molecules attach themselves to the ions, and because water molecules are constantly moving, their motion will actually cause the ions to separate from each other and pull away, dissolving. How much can you dissolve? Well, it depends on a couple of things. First of all, how many water molecules do you have? Because the more water molecules you have, the more stuff you can put into it. Also, how fast are the water molecules moving? Because the faster they're moving, the fewer water molecules it's going to take to tear the ions apart. So there are a few factors that can affect how much can dissolve. Because the particles are dispersed on the atomic or molecular level, there's no filter paper that's small enough to stop the particles from going through it. You cannot separate a solution by filtering it, because the holes in the filter paper are just too huge to stop any of these small particles from just passing right through it. Also, because the particles are so small and so far apart from each other, light can't reflect off of it. There's just nothing for light to bounce off of. I mean, you see this beam of light, right? Hitting the screen, you actually see the beam of light? Of course not, because air molecules are too small to reflect light. But if there's some dust in the way, you can see it. On the molecular scale, the particles are just too small to bounce light off of, which is why you can see right through a solution. They're transparent. Also, because the particles are dispersed evenly on the molecular level, it's homogeneous. And the only way you can separate a solution is by getting rid of the solvent. You see, salt has a very high melting point, about 1074 Kelvin. Water, though, boils long before that. Water boils at 373 Kelvin. So if you heat this mixture up, when you hit around 373, it's actually going to be a little higher than that because of something called colligative properties. We'll look at that later. The water molecules will have enough energy to escape and break free. And when you evaporate or boil off the water, all that does is leave behind these ions, which are attracted to each other, and come back and reform the original solute. So you can separate a solution by evaporating or boiling off the solvent. Now, if water didn't have partially positive and partially negative charged ends, there'd be nothing to attract these positive and negative ions. In order to dissolve things that have charge, your solvent needs to have charge. In other words, like dissolves like. Polar solvents, like water, are capable of dissolving things that are charged, like ionic compounds and other polar molecules. However, as you know, water and oil don't mix. It takes a nonpolar molecule to dissolve a nonpolar solute. For example, this molecule here called benzene, look how many lines of symmetry this thing has. I mean, it is loaded with lines of symmetry. It's just crazy with them. You could say, actually, this is like one of the most ultimate nonpolar solvents. It's so nonpolar, it can even dissolve plastic, which is also nonpolar. This is carbon tetrachloride, which is also a nonpolar molecule. Carbon tetrachloride was used in the dry cleaning industry, except they found out that it was carcinogenic. And, you know, if you can get cancer from washing clothes or wearing clothes, probably not a good thing. Nonpolar solvents are very handy to use in glues that are meant to hold nonpolar things together. So polar things can dissolve polar things, but nonpolar things can't dissolve nonpolar things. That's why you can pour water into a plastic cup and the plastic doesn't dissolve, because the plastic's nonpolar. Now, how much solute can you dissolve in solvent? Well, like I said, it depends on how much solvent you have. Reference table G gives you the solubilities of different kinds of solutes at different temperatures, assuming you have 100 grams of water. If you have 200 grams of water, then you just double all the values here, because 200 grams of water can obviously hold twice as much as 100 grams of water. So holding the grams of water steady at different temperatures, we can dissolve different amounts of different solutes in that 100 grams of water. Now, there are two things that we need to look at. Entropy being the most important. When you dissolve something in water, its entropy will either go up or down depending on what phase it is that you're dissolving. If you dissolve a solid into water, the solid becomes like a liquid when it dissolves. Therefore, its entropy increases. This is favored at high temperatures. Increasing the temperature on a solid solute is going to increase its solubility. But for gaseous solutes, gases already have high entropy. When you dissolve them in water, they act like a liquid. You're bringing their entropy down. That's not favored. Therefore, this will only be favored at low temperatures. Lower the temperature, increase the solubility. And so you can see what we've got here. The curves that go up are solid solutes, and the curves that go down are gas solutes. HCl, hydrogen chloride gas, gets less soluble as you increase the temperature. Why? Because its entropy change is not favored. And the higher the temperature, the more unfavored it is. Here, for sodium nitrate, which is a solid, when you dissolve it in water, its entropy change is favored, going up in entropy. And increasing temperature just makes it even more favored. So solids get more soluble as temperature increases, and gases get less soluble as temperature increases. So what's another way you can get a gas to dissolve in water? Change the pressure. If you increase the pressure, you will force that gas to dissolve. Increase the pressure, you will increase the solubility. This is why when you open up the top of a bottle of soda, the CO2 comes out. Not because the CO2 is just sitting there waiting to escape, but because when you lower the pressure,